In this video, you're going to see how I spent nearly an entire month getting a single ring to display on the Amiga from Sonic the Hedgehog. But what you're also going to see is all the gory details in terms of how we got there and why we're in a very strong position now to move forward with the rest of the game. So, if you cast your mind back a month, I'd just got a level of Green Hill Zone scrolling on the Amiga using the dual Playfield mode. However, I wasn't particularly happy about the way things were going. Dual Playfield mode comes with some serious compromises. You've got 16 colours you can use for the background, then you've got 16 colours you can use for the foreground. However, those foreground colours also have to be shared with the sprites. And not only that, there were certain colours I wanted for the palette rotation for the water effects. And the game was going to become quite compromised by having to operate within those 16 colours. Thankfully, shortly after the video, I experimented with a new approach inspired by some of your feedback. This new approach used AGA's SScan2 register, which causes the Amiga's sprites to repeat every 256 pixels horizontally. Using this method, I created a full parallax scrolling background, deploying a combination of copper, trickery, and 4 repeating sprites. Each AGA sprite is 64 pixels wide, utilizing a 16 color palette. Therefore, we end up with 256 pixels horizontally repeated with the SScan register. There are compromises to this approach. It limits the background to a repeating width of 256 pixels, and due to a quirk of the Amiga hardware in AGA mode, sprites can't easily be drawn to the leftmost area of the screen. But the big advantage is we've retained a fully independent scrolling background layer that barely uses any CPU time, plus we can increase the number of colours available for the foreground layer and the Mega Drive sprites to 32, whilst at the same time reducing the overall number of bit planes from 8 down to 5. This is definitely the right decision, because Sonic is a sprite-heavy game, as we shall see, will need all the memory and blitter bandwidth we can get. You're watching this running on WinUAE with the CPU underclocked to 7 MHz, just to prove that this is performant. Last month's code simply crashed at this clock speed because I was trying to do way too much in the vertical blank. In fact, I've completely overhauled the internals of the Mega Drive rendering engine to work on the Amiga. One of the few hardware advantages the Amiga has over the Mega Drive, for Sonic in particular, is a lot of memory. Well, 2 megs on a stock A1200. Rather than dealing in 8x8 tiles as before, the rendering has been reworked to directly cache and blit the larger 16x16 blocks that Sonic usually creates on the fly. These blocks are created and cached on level load, and what's more, this includes horizontally flipping the data where necessary, a massive performance saving. Drawing a block has become a simple blitter operation that occurs as each column or row scrolls onto the screen. So typically, if we're only scrolling in one direction, we'll only need a handful of blits. Although it visually looks similar to before, under the hood there's tons of new assembly code. My style of programming is always to get it working and then to optimize it afterwards. So although things visually look very similar, the code under the hood has been completely replaced and re-engineered. Believe it or not, the most complicated part of this tile rework was actually getting the flowers to animate. These are animated tiles. In Green Hill Zone, animated tiles are used for the flowers and the crest of the very beautiful waterfall. The reason these prove very complicated is that we no longer have a tile map. On the Mega Drive, tiles are animated by effectively just writing to the tile data and swapping it in and out. And because the entire tile map refreshes every frame, you get animation extremely cheaply. But if you think about our Amiga rendering approach, Our only opportunity to change what is being rendered is at the point where graphics scroll onto the edges of the screen. We don't have the graphical horsepower to refresh the entire screen every frame. So once a flower ends up stranded in the middle of the screen, there is no memory that it's even there. It's simply been rendered to the playfield and forgotten about. The only time it will be registered again is if we were to scroll the flower off the screen and back on again. If I drop in the Mega Drive code to update the graphics data, nothing would happen. The flowers wouldn't animate. So how did I solve this? Well, if the only place the engine can identify an animated tile is at the point it initially renders a new row or column, then we can modify that area of the code to check for a matching block of data that contains an animation. But wait, we don't really want to be iterating through a long list of blocks one by one every render call to detect a match. That would slow down the rendering engine. The optimal solution was to write a quick Python script to parse Sonic's level data and set a bit on any block that contained an animated tile. By doing this, we've moved the complexity outside of the rendering to a one-off script I've run on my PC. All the rendering engine now has to do is check a single bit when a new block scrolls onto screen and divert rendering to our custom animated tile handler. The animated tile handler is around 500 lines of brand new assembly, which completely replaces the original Sonic code. When a block containing an animation is identified via the modified level data, this handler maintains an active list of animated items currently on screen. Every frame it checks the list to ensure the animated graphics are still visible. This list also records the world coordinates of the animations so we can track where they are. We can then process the items in the list and directly modify just those areas of the screen that we need to change. Now, when I started this project, I foolishly thought that probably the most complicated aspect was actually going to be doing the scrolling, but I'm now beginning to rethink that naive assumption, and maybe it's just because it's what I'm looking at right now, but I'm now thinking that sprites are going to be a lot harder. And the reason is that sprites are used across the board in Sonic. They're not only used for the obvious things like Sonic and the enemies, but they're pretty much scattered across the entire level and baked into the scenery as well to do all kinds of like interesting modifications to the landscape. I've been working with Retro Rick on some of the artwork for Sonic and wrestling it back into a format for the Amiga, and he started pointing out to me that there are parts of the level that are actually just made of sprites that are patching over elements of the background to give them a more pseudo 3D look. So as I'm getting into sprites, I'm kind of thinking I'm going to have to divide them into separate categories whereby you've got static sprites that are part of the level that I can maybe bake onto the playfield, and then you've got your freely placeable moving objects which are a lot more sophisticated, and maybe they actually get piped through a separate rendering pipeline to handle them. But I'm getting ahead of myself here. Let's quickly cover how sprites work on the Mega Drive. The Mega Drive has a sprite layer that can render up to 80 sprites simultaneously. Sprites are independent from the underlying planes. As a programmer, it's very easy to draw and move a sprite with minimal CPU usage. You just need to set up the sprite hardware with some relatively basic values like the sprite size and screen coordinates. Transparency, clipping, and scrolling are all handled for you by the hardware. Not so on the Amiga. The Amiga has 4 sprites in 16 color mode, and we're already using those for the background layer. Now, I know I've already implemented sprites for the title screen, but that was before I optimized the rendering, so I need to explain why this is much harder for the in-game engine. Reason number 1, playfield destruction. Let's say I draw a sprite to the playfield. On the Amiga, I've now effectively written over what you see behind the sprite. It's gone. So if I don't solve this problem, as a sprite scrolls around the screen, it's going to leave a blurry trail of itself behind. Visually cool maybe, but not helpful. So how do we restore the original background without redrawing the entire screen? You might think the best way is to save a copy of the section of the background before drawing over it, and you'd be partially right, but Sonic is a game where the background scrolls and the sprite scroll independently. If we were to just copy the background behind the sprite, it won't be the same one frame later, and the background would have moved, so it would look incorrect. And this is where the scrolling technique I chose in the previous video comes in handy. I mentioned it wasn't the optimal scrolling technique when considered in isolation, but combined with lots of sprites, it's incredibly useful because the scrolling algorithm effectively renders new columns twice. So we actually have the same screen twice in memory. When we render a sprite, we can check where the current viewport of this screen is. We then blitz sprite data to the currently visible area, but we can also always restore the underlying data from our pristine copy. So reason number 2 of what makes sprites tough to implement: clipping. On the Mega Drive, if you want a sprite to render partially off screen, you can simply plot it at a location outside of the display window, and if it's tall enough, you'll see the relevant parts popping into view. But think back to how we created an infinite scroll on the Amiga in the last episode. We're using the copper to reposition the playfield mid-frame for the vertical scroll. This means that sometimes what you see is 2 sections of the playfield joined together, even though that data isn't contiguous in memory. We have to detect when a sprite starts rendering at the end of the playfield in memory, but needs to wrap back to the start, even though it will look seamless on the screen. And we have to use a similar technique if we want to display a sprite that's partially outside the edge of the playfield. Now, if all this is beginning to blow your mind, hurt your head, and you've just lost track of what on earth I'm talking about, don't worry, because you're probably not alone. It hurts my head too. The point I'm trying to make here is that it's really difficult to retrofit all of this stuff into an existing game engine that has certain expectations about how things are going to be structured and set up. The final challenge is ensuring transparency is adhered to. This isn't complex on the Amiga per se, although it's not enough to presume Pixel 0 is transparent as per the Mega Drive. We need to provide additional data so that the Blisser handles transparency in the form of mask data. The complication lies in modifying Sonic's sprite code to handle this extra data. Sonic's engine manages sprites through a system called pattern load queues, where new sprite data is loaded and uncompressed over a series of frames for speed. Shoehorning this change in and debugging all the problems it caused was convoluted. Anyway, I'm delighted to say that all of the above is now implemented, and even though all I've got to show for it is this stupid ring, and I was probably foolish for thinking that I could get there faster than I did, I am kind of confident that the rest of the sprites are going to follow a little bit more quickly in terms of getting them into engine now. I've done a lot of the hard graft and the groundwork. You'll recognize this ring as belonging to the debug mode from the original Sonic, which was a hidden part of the game, which was effectively like a little level editor the developers left in. So I've started implementing that. Any project of this scale needs some tools to manipulate levels and graphical data. Thankfully, Sonic already has some cool fan-made tools in the form of the Sonic LVL level editor and Flex sprite editor. We can use Sonic LVL as is, but Flex needed modifications to transform its output to be Amiga friendly. I added new functionality to Flex so that it could import indexed PNGs from Photoshop and work with our modified Amiga sprite format, which now uses any colour from a 32 colour pool, or 5 bits per pixel. We also needed sprite data output in the interleaved bitplane format that Amigas use, not the standard Mega Drive format. So the pipeline effectively becomes Mega Drive data in and Amiga data out. Now, as part of this project, I always like to be fully transparent about how I'm approaching problems and getting things done. For the game code itself, I always code everything fully by hand. That's part of the fun for me. This is a hobby. I like doing so. I like having that granular control over optimizations and understanding how each line of code works on a per cycle level. That's part of the attraction to doing something like this. But there are areas where I do use AI, and I think it's always important to be clear where you do. And one area I found it really great for is getting up to speed fast on the tools. For example, these are old code bases that maybe haven't been maintained in recent years, and AI can help you get the code base compiling, it can help you understand the code base quickly, and it can help you modify features really fast. And in the case of the tools, I wanted to get something in Rick's hands that he could use relatively quickly. I didn't want to spend a month learning a programming language and getting up to speed. And these are ultimately tools that were written by someone else in the first place. So I'm kind of standing on their shoulders and benefiting from their existing work. So I think it's just important to be transparent that for the tools, I've modified them with AI. I'd also like to give a really big shout out to Retro Rick, who's been helping me on the project in terms of wrestling the Mega Drive palettes and graphics onto the Amiga. He's got a really fantastic YouTube channel with loads of interesting projects, so please go and check that out. I'll put the link in the description. One side quest I've embarked upon is audio tooling. I'm writing a nifty program that will take the original assembly audio files that define Sonic's music and convert that original data into Amiga mod files. I already have a partially working prototype of this, and it will be the subject of the next installment, as it deserves an entire video to itself. Speaking of audio, if you enjoyed the previous Outrun project, then keep your eyes peeled on your YouTube notifications on Friday the 6th of March, because there's going to be a special announcement. As always, thank you very much for watching the video, and I'll see you in the next one. And check out some of my other videos if you haven't already.